Electrophilic aromatic substitution. So this is a common reaction of aromatic compounds. I have taken here benzene ring and we will consider these electrophile. Electrophile is electron deficient species, lack of electrons. E plus means electrophile, which is electron deficient species, lack of electrons. When this is reacting with the aromatic center, we have considered here a benzene ring where on each carbon there is hydrogen. So you have to select any one of these 6 hydrogen. So what happens? Hydrogen is replaced with E. You can see here. Now this E means electrophile is taking the position of hydrogen, and this reaction is called electrophilic substitution reaction. So the replacement of hydrogen of the aromatic ring by the electrophile is called electrophilic aromatic substitution reaction. Here in case of benzene, we have to consider only 5 very popular reactions. First is halogenation. So we will discuss them in more detail. But now at the beginning, so when halogen is actually used as an electrophile, means E plus or Br plus, Cl plus means E plus means Cr plus and Br plus. So when these electrophiles actually replacing hydrogen of the aromatic ring, we get this product. So replacement of one hydrogen by the X means Cl or Br, we get halogenation reaction. For this reaction, we need FeX3. This is required. If we use FeX3, then and then only we can generate E plus ion, C plus, Cl plus or Br plus. So FeX3 is required. Next reaction we are going to discuss is the nitration reaction, where replacement of hydrogen of the aromatic ring, here in case of benzene, by the NO2 group, NO2, then this NO2 is generated from this nitrating mixture by using HNO3 and H2SO4. This mixture is called nitrating mixture. When this NO2 is produced, that will replace hydrogen of the aromatic ring and we get here nitro compound. So here E plus means electrophile is NO2 plus. Next reaction we are going to discuss is sulfonation reaction, where hydrogen of the aromatic ring is replaced by SO3H group, and that SO3H group is generated by using this mixture H2SO4 and SO3. This mixture is also called oleum. This reaction is called sulfonation reaction, where hydrogen is replaced by SO3H group. So here E plus is SO3H plus. This is our electrophile. Next reaction, I have purposefully written these 2 reactions separately. Fourth reaction is Friedel-Crafts alkylation, in which we replace hydrogen of aromatic ring by R, means any alkyl group. So for that purpose, we are using RCl, alkyl halide, alkyl chloride, and one catalyst we are using, that is anhydrous AlCl3. So here R is going to replace this hydrogen and we get here R on the benzene ring, and here electrophile is carbocation, R plus is carbocation. Next allied reaction is a Friedel-Crafts acylation. Same catalyst we are using here, AlCl3, and we are using acid chloride. So this acid chloride is used. From this acid chloride we can have this RCO group, and that RCO group is going to replace hydrogen of the aromatic ring to get this substituted product. So we get this substituted product. Here electrophile is this RCO plus. So a positive charge is there on this carbon, on this carbonyl carbon. So in this way we are going to discuss all these 5 reactions in more detail. We will discuss general mechanism of all electrophilic substitution reaction, means halogenation, nitration, sulfonation, alkylation, acylation. All these reactions are actually following this mechanism. So we will see how reaction occurs, what is the path of that reaction we are going to discuss here. Now, this is actually electrophilic substitution reaction in aromatic compounds is actually two-step reaction. First step is electrophile attack. So I have not considered here how that electrophile is generated. That will be vary from reaction to reaction. So we assume that the electrophile is generated. Now E plus is electrophile. It attacks benzene ring because, or any aromatic ring, because there is a pi electron cloud circulating below and above the ring, and this is electron deficient, so it is attracted and it attacks. So if this electrophile wants to form bond with this ring, we need a pair of electron, and that pair is taken from pi bond. So you have to remove, if you want to join this E here, so you have to remove this pi bond outside. So if I take this pi bond and remove it outside, just like here, remove it outside, so you can check the formal charge of this carbon. I mean this carbon which is just generated when this pi bond is now used to join this incoming electrophile. So on this carbon there will be 3 electrons and we need 4 electrons for neutral carbon. So because of this, positive charge is developed, positive formal charge is developed here on this carbon. So this is carbocation. Now this carbocation can undergo different resonating structures. Resonance is possible. How? Simply you have to move this bond, adjacent bond. So you can see here, you check this bond and move this bond in between these 2 carbons. So I have shown here which carbon. You have to just move this bond, which is also shown by this curved arrow. So if I just move this bond in between these 2 carbon, similar kind of structure you can see here is developed here at this carbon. So positive charge is actually migrated from this carbon to this carbon. Now you have to move this bond which is at the adjacent position in between these 2 carbon, which I have shown by using 2 red dots. So if I do that, this bond is now here. This bond is moving here in between these 2 carbons. And the similar structure is developed here at this carbon. So in fact, this positive charge is migrated at this carbon. So the positive charge which is responsible for the destability, which is not actually a good sign, because aromatic ring is a stable compound, and when electrophile attacks and when this bond is moving outside, so that 6-pi system is disturbed. That means this is no longer aromatic. So if aromaticity is disturbed, this is a slow reaction. So our aromatic ring is not actually willing to form this kind of reaction. So this is actually a rate determining step. So the rate of overall reaction is depend on the step 1, because step 1 is a slow step. Why it is slow step? Because aromatic center is disturbed. Aromaticity is not there. And now see, this is stabilized. Although it is unstable, but this carbocation is stabilized because this positive charge is now shared by 3 carbons. So here, here and here. So actually at each carbon there is a positive charge plus 1 by 3. So this is less than 1. So plus 1 by 3 here, plus 1 by 3 here, plus 1 by 3 here. So there is no complete positive charge on any carbon. So this is a fraction. This is in fraction. 1 by 3 means fraction, less than 1. So the intensity of positive charge is less. Because of this, this is more stable carbocation, and this is the driving force why this is happening against the aromaticity. So this is actually the explanation. If you want to draw, it's a resonance hybrid combination of all these. That means no bond is double bond, complete double bond, and no bond is complete single bond. So I have shown that bond which is being broken here in every resonating structure by using a dotted line. And the positive charge is not complete positive charge. Positive charge is here at this carbon, but in next structure that positive charge is vanished. So there is no complete positive charge, that is partial. So this is partial positive charge. So the positive charge is developed here at this carbon, at this carbon, and at this carbon. So in this way you can draw the resonance hybrid for all these resonating structures. Now moving toward the second step, which is very fast. Why? Because anyhow this molecule will try to remove its proton, or will try to remove its electrophile, because it is now ready to have aromatic center, or it will try to regain its aromaticity. It can be done by two ways. One is either it can remove this E or it can remove H. If the reaction medium having base, it can remove this H immediately, because you can see, because of this positive charge, the acidity of this proton will be increased little bit, so this base can remove that proton more easily. So as soon as this carbocation is formed, this base is now doing its work. It will remove this proton, and the bond which is now joining this carbon and hydrogen will move, will form a pi bond, will move inside. So this bond is moving inside to form a aromatic center, to form that 6 pi electron system. So once that 6 pi electron system is regained, so stability is regained. So this is a driving force. So the step 2 is a more fast step. Now the energy related to this reaction, energy related to first step and second step, you can draw here by using this energy diagram. So on this axis I have taken here energy. So this is the energy of our starting compound, this benzene ring. Now once that reaction is started, this is the first energy barrier which should be overcome if you want to have that reaction or that product. So this is our first energy barrier, which is called energy, activation energy. That much energy is required to form our transition state first. You can see here a transition state first, means which bond is being broken, which bond is being formed, that we have to show by using a dotted line, because this is hypothetical. Now see here, we cannot isolate this transition state. So this is an energy barrier. So this compound is converted to the product, and for that purpose it must have that much energy. So EA, this activation energy should be there, otherwise there will be no reaction. So after this transition state 1, the molecule is converted here, molecule is coming here. You can see the energy, decrease in energy. So this is what the energy of this carbocation. Now again, this hydrogen is removed, but this is next step. So to remove that hydrogen, there is another energy barrier, so which is actually the transition state 2, which is shown here. So you can see here that hydrogen bond is being broken. Now that this energy of activation EA2 is required for second step. So there are two in this electrophilic aromatic substitution. There are two energy barriers, and after that it is converted to the product. So this is the product, or the energy of the product, you can see here. So you can even calculate the energy gap between the starting material and the product, and this is all about energy diagram. So in this way, all these 5 reactions, all these 5 electrophilic substitution reactions in aromatic ring actually going to follow this path, going to follow this mechanism. That's why it is called general mechanism. Thank you.